All right, Tyler, I totally understand what you were asking. I did not understand what you were asking before. I'm really glad I had you email it to me, your question. So, um, and I think I have the answer for you. If I don't answer your question fully, then let's meet tomorrow and sometime. Do I have you tomorrow? No. Um, yes, I do. So let's meet tomorrow during class and we'll discuss it more. But the idea is, so you take you have a Taylor polynomial, right? So t n of x, or rather, um, let me start somewhere else. The idea behind Taylor series is that we can take some elementary functions and represent that with some Taylor polynomial, Taylor series, I should say, right? So, and that the Taylor series, as n goes to infinity, the series itself is going to accurately approximate that function around some point. So when we write out the Taylor polynomial, which is just a portion of the Taylor series, so I guess here, this would be, ooh, that's a really big eraser. There we go, okay. So this would be like infinity. So a function, some elementary functions can be approximated, or can be represented, I should say, not approximated. So elementary functions can be approximate or represented by a Taylor series that goes to infinity, right? But if we want to represent an elementary function with a polynomial, because we don't want to have to, keep plugging in a bunch of numbers for forever, there's bound to be some kind of an error, right? So here's our polynomial. So we'd have, f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial, and so on and so forth, right? Well, okay, so we would go down to plus f to the n prime of a x minus a to the n over n factorial, right? Okay. So the idea is that we would stop there, but really the Taylor polynomial continues on. So what would the next term be? Well, the next term would be the f n plus 1 derivative of a times x minus a to the n plus 1 all over n plus 1 factorial, right? So that's the next term. So the idea is that we're going to have an error because we're kind of like truncating it right here. We're going to have some kind of an error from the actual value of the function. And that error we can't find exactly what that is, actually, because we know, you and I both know, I think, that this doesn't, I mean, there's more there. If it's a series, it goes to infinity. There's more terms after that even. So this doesn't even represent the full amount that you're going to get, but it gets you close. And so this is just an approximation. And so how we get close to that is, instead of saying f of n of a, or the n plus 1th derivative of a, we say of z, where z is this like maximized value, right? So that we can try and get kind of like the maximum error that we can find just by having to look at one more term. It is really the idea behind that. So I hope that makes sense. I think that's everything I wanted to say. Here, let's put this over here. But yeah, so I hope that makes sense. And, we have these thingies, all that stuff. And again, let me know. Well, let's meet tomorrow during class. All right, bye.